Welcome back to Engineering Acoustics. Hi, this is Professor Brian Harne. When a sound source is turned off in a room, the sound levels decay with time due to room absorption. In this video, we'll learn how to quantify this absorptivity in rooms, and we'll learn what makes a good sound absorber.
So let's get started. We know that the usability of a room is determined by its reverberation. In areas where performances are conducted, we seek ambiance in the reverberation, while in rooms where clear communication is required, the reverberation must support intelligibility of speech. So for instance, in auditoriums, we expect that the reverberation may be greater than that in classrooms. And as we look at these example images on the right, we see many types of materials and surfaces. The classroom contains many hard, reflective surfaces like the blackboard, the floor, the desks, but it also contains absorptive ceiling tiles. So considering all of these materials, how does the room compensation overall work to affect sound reverberation? We know that the reverberation time, T60, is in inverse proportion to the room absorption by our T60 equation, which is equal to 0.161 times the room volume divided by the room absorption A. And the total room absorption is equal to the product of the room surface area, S, room surface area, and the total absorption coefficient. A is equal to S times A bar. A bar is the total room absorption coefficient. Part of this acoustic energy is absorbed in the material and part of it is transmitted. So absorption is partly a transmission and dissipative phenomena. The total room absorption coefficient is contained between 0 and 1. Since it has no units, it's a normalized factor. So that means our T60 can be written as equal to 0.161 times the room volume divided by S A bar. Now, for most materials, the room does not contain one surface treatment. The room is a combination of many surfaces, each having different absorption coefficients. So the total room absorption coefficient is an area-weighted average, where we have 1 divided by the total surface area of the room is equal to a sum over index I of SI, the individual surface area, and AI, the individual surface absorption coefficient. And this is for each octave band. So for instance, this living room contains a couch, hardwood floor, wall, window, and so on. If we consider all of these surfaces, we find the primary factors. Lots of surface from the floor, from the walls, especially the window, a very reflective glass. But we also have a rug and a couch, and even some frames on the wall, which are very different in reflectivity or absorptivity than the drywall itself. So knowing the variety of surfaces and absorption coefficients in a room, how do we compute the reverberation time? Let's consider the following room with all of the dimensions shown in the schematic in meters. We've got a room with a wooden floor, and over a portion of the wooden floor we have a heavy rug or carpet with undercarpet, window panes, painted drywall all around, including the 2 walls and ceiling that are not shown, and finally a glass heavy plate, which is similar to a big screen TV. Our goal here is to find the reverberation times in the 250, 500, and 1 kilohertz frequency bands. Now, we use our area averaging for the total room absorption coefficient, and then our T60 equation for each octave band. We can search online or in any variety of textbooks to find tabulated lists of the absorption coefficients for the different materials. So for the absorption coefficient at 250 Hz for drywall is 0.15, and it goes down to 0.1 and then 0.05 as we go up in frequency to 1 kilohertz. Whereas for carpet, the absorption coefficient is 0.25 and increases as we go up to 1 kilohertz. Using our area average for the total room absorption coefficient, we can ultimately compute the reverberation time T60 at 250 Hz and see that it is 0.62 seconds. At 500 Hz, it's slightly greater, 0.64 seconds, and at 1 kilohertz, it's 0.76 seconds. In other words, this calculation is fairly straightforward, given knowledge of the dimensions of the room, the distinct surfaces in the room, and knowledge of the absorption coefficients per octave band. But how do we compute these absorption coefficients if we make a new material or put some new treatment in the room? Determining the absorption coefficients is fairly simple. We determine this in a reverberation chamber, where we might use a professional room with sound diffusers like we see in the top right, or any room with a considerable reverb time. A bathroom at home is an excellent space to compute the T60 and absorption coefficients of materials. Just pull back the shower curtain, take out any soft bathroom mats, and all of the surfaces in that bathroom are likely very reflective with low absorption coefficient, making this test as accurate as possible. The first step in this test is to measure the T60 for the room alone. This gives us a value of the total room absorption coefficient that we'll call A0. The next step is to measure the T60 in the room with a new material that covers part of the room's surface. We see in the example on the right that the test sample is sitting on the floor, so it exactly covers the part of the room and doesn't artificially introduce new area. If we're trying to measure the T60, for instance, of a couch, we might need to move the couch into a corner of a room like this. The absorption coefficient in a given octave band, A sub s, of that unknown material, is equal to then A0, the total room absorption coefficient, without anything in it, coefficient originally, plus S, total room surface area, divided by S sub s, surface area of material, multiplied by A0, multiplied by T, the T60 originally, divided by TS, the T60 after we apply the treatment. This technique is computed for each T and T sub s in different octave bands to compute the A sub s, the absorption coefficient of the test sample, in each octave band. This process is used by many companies and is tabulated all across online databases as well as in textbooks. You'll find absorption coefficients for many common building materials, interior materials, and so on. We often report these absorption coefficients only from 125 Hz to 4 kHz. And this is because these absorption coefficients and these frequencies are most important to understand and articulate the details of speech and music. So for instance, let's look at a few examples. Fiberglass. Fiberglass fills the walls of many building constructions because it is a thermal barrier and also absorbs sound. We see that as the fiberglass material thickness is doubled 2 times, from 1 inch to 4 inch, the absorption coefficients all go up. At low frequencies, the doubling of thickness either doubles or more than doubles the absorption coefficient. But at high frequencies, the absorptivity of the fiberglass, even at 1 inch thick, is already high, so that doubling the thickness only draws closer to a perfectly absorptive 1.0 absorption coefficient. Now for concrete is a great barrier, since it is good to stop sound. Unpainted concrete, in fact, is also a good absorber of sound, since it is a porous material. The absorption coefficient of concrete is around 0.3 across the board in the octave bands. But if we paint the concrete, we paint and cover over all of the pores that absorb sound, so that the absorption coefficient of painted concrete is very low. In fact, it's similar to the absorption coefficient of drywall on studs. Excepting at low frequencies, drywall is very reflective and reflects back a lot of the sound that is incident on it. The glass window pane, on the other hand, is slightly more absorptive of sound. This is due to the fact that many glass window panes are a 2-ply layer of glass with an air gap in between that's specifically designed to stop and absorb sound. What we see in general is that barriers, hard, stiff materials, these have low absorption, while soft materials have very high absorption. Now, contradictory to some intuition, we would never want to use absorbing materials like fiberglass to block or stop sound. While fiberglass is very absorptive, that does mean that the sound keeps going through it. So if we want to block sound, we need to use a dense barrier. So let's summarize what we've learned. We know that sound in enclosed rooms is absorbed by porous materials, and the most dissipative absorbing materials are those that create tortuous paths for sound to travel from one side to the next. So for instance, fiberglass with randomly oriented fibers requires sound to find a way through all of these fibers before it gets to the other side. This creates added dissipation in addition to the great absorptivity. The reverberation time of a room is easily estimated based on knowledge of the materials in a room, and changing materials in the room may help us meet any recommended T60 values, for instance, for its speech intelligibility in a classroom. Estimating the absorption coefficients for new materials is also readily undertaken using before and after reverberation time testing.
That's it for this video. Now that we've learned how acoustic waves build up in a room with sound sources, in the next video we'll learn how these sounds may transmit to adjacent rooms.